Perfect. So it is a pleasure to present Kiran Kedlaya from the University of California, San Diego. He will speak about Drinfelds Dilemma for F-isocrystals.
All right, thank you to all the organizers for the opportunity to speak, and at least for, in theory, giving us the opportunity to all visit Buenos Aires. I'll have to find some other time to come. So this is a project that is in progress, although I have a draft on my website, and part of it is joint work with Daxin Xu from the Morningside Center. Let's see. So these slides are posted on my website, so you can go have a look at them if you want to see, look back at my slides. There are funders, and my university sits on unceded ancestral land of the Kumeyaay Nation, but they have their own website, so I don't have to tell you more about that. All right. What is Drinfelds Dilemma? So in this talk, I'm going to fix a prime P. We're going to be talking from the point of view of the Langlands program. We're going to be talking about the function field situation in characteristic P. Now, X is going to be a smooth FP scheme. It's not necessarily a curve. X will be playing the role of some other thing, like a moduli space of Stukas. X is going to be an algebraically closed field of characteristic P, and phi sub k will, well, sometimes it will denote the Frobenius map on K, but most of the time it will denote a map on xk, the base extension of X from FP to K, which is the map that sort of acts trivially on X and was Frobenius on K. So if you can think of this as some sort of relative Frobenius if you want. So in this business, it's customary to call this a partial Frobenius, because it's doing xk is the product of X and K over FP, and phi k is performing Frobenius on the K factor, and it's the identity on the X factor. So that's the sense in which it's a partial Frobenius, and you'll hear me using that term as we go along. So I like to think of Drinfelds lemma as a meta principle, which is that there's a map from X to this formal, if you like, category theoretical quotient of xk by a discrete group generated by the partial Frobenius. And this is not an isomorphism, but many structures are preserved by this map. So we'll see a bunch of statements that equate structures on X versus structures on xk divided by phi k. And I'll tell you as we go along what it means to define structures on the right-hand side. But you should think of this as a quotient by a free group on one generator, and so structures on this right-hand side are kind of equivariant objects for the action of that partial Frobenius. Okay, and I claim this plays an important role in the Langlands correspondence. We'll come to that in a couple of slides. So one concrete statement that is sort of comes under the original class of statements proved by Drinfeld is that the finite etale coverings of X are the same thing as the finite etale coverings of xk divided by phi k. In other words, if you take a finite etale covering of xk equipped with an isomorphism with its phi k pullback, well, you can get one of those from a finite etale covering of X, and that pullback functor is an equivalence. So, okay, I'm not claiming that these two are somehow the same, but they have the same finite etale coverings. So they're related in that way. Another way in which they're related is that the category of, well, I probably don't need quasi-compact here. Well, I didn't assume X was finite type. So let's say quasi-compact. Open emergence into X is equivalent to quasi-compact open emergence into xk, again, equipped with an isomorphism with the Frobenius pullback. So roughly speaking, open subsets of X are the same thing as equivariant open subsets of xk. So these two statements are both somehow telling you that the topology of X, either Zariski or etale, is similar to the topology of xk divided by phi k. Okay, so how does this play a role in the Langlands correspondence? Well, let's consider a prime L not equal to P. You can deduce from what I just said that the categories of least QL sheaves or QL bar sheaves on X and on XK divided by phi K are equivalent. So a least sheaf on XK mod phi K is once again a least sheaf on XK equipped with an isomorphism with Frobenius with phi K pullback. And similarly for constructible derived categories. So to go from least to constructible, use the fact that stratifications that are on XK, which are phi K equivariant, come from X using this, that uses the second part of the assertion. For least sheaves, you somehow only need this first statement, but to do constructible ones, you need both. And if you look in section 8 of Vincent Lafforgue's paper on Stuttgart-Purley groups reductifs, then there's this key step in his construction of automorphic Galois for reductive groups where you define these excursion operators, and somehow this uses in a very essential way this this comparison, maybe at the, let's say at the constructible level. So this is, I mean, this is in some sense implicit already in Drinfeld's work for GL2, but you see it much more explicitly in Vincent Lafforgue's work. And well, you know, if you know me, I always prefer to take L equals P, and instead of working with etale cohomology, I want to work with some sort of p-adic cohomology, some kind of rational crystalline cohomology, if you like, or more precisely, Berthelot's rigid cohomology. And well, we more or less know how to set up a kind of p-adic analog of this proof by Vincent Lafforgue, because Tomoyuki Abe worked out a lot of key details when he was transcribing Laurent Lafforgue's paper for GLN. So there had been a lot of work done prior to that, setting up kind of the ingredients for a six functors formalism for p-adic coefficients. And Tomoyuki was able to describe a category that has a six functors formalism and that he was able to work with. But the thing you still need if you want to deal with reductive groups is you need an analog of this comparison of constructible derived categories in the L-adic case. And in particular, you need the comparison of least sheaves, which is not an immediate consequence of what we already know. So the goal of this talk is to tell you why it isn't a consequence of what on one hand, it's not an immediate consequence of what we already know, but on the other hand, it is ultimately a consequence of what we already know. So that's the goal of the present work. So that's the last appearance of automorphic forms in this talk, I'm afraid. We're mostly going to be talking about p-adic cohomology from now on, but hopefully that was some motivation. Okay, I'm watching the chat in case there are questions. Of course, you can always also interrupt if you have any, but I don't see any and I don't hear any, so. Continue. Okay, so for the purposes of telling, I need to tell you what a coefficient, what the analog of a least sheaf is. So I'm going to tell you, there are actually two analogs of a least sheaf in p-adic cohomology. One of them is easier to describe, and one of them is the better object to work with in the long run. So first, let me tell you about the easier to describe one, and then we'll come back to the one that's better to work with at the end. So the one that's easier to describe is a convergent F-isocrystal. So to describe one of these things, let me just assume that X is affine. There's a globalization step that happens at the end of this definition. Or you can also do this in a more site-theoretic way, but for purposes of giving talks, it's nice to have a concrete description. So what you do is you assume X is affine, and you make an artificial choice for the purposes of exposition. You make a choice of a smooth formal lift of X from FP to ZP. And then your convergent F-isocrystal consists of the following data. You take a vector bundle on the Renault generic fiber of P, which, since we're talking about affine things, is just a finite projective module over the ring of sections of P with P and capital P with small p inverted. So, but I like to think of it geometrically. So it's a vector bundle on this rigid analytic space. and I have an integrable connection on this rigid analytic space. So this is defined in terms of the continuous differentials on the Raynaud generic fiber. So I have a vector bundle with a connection. So this is basically an isocrystal, but now there's a Frobenius action, which is an isomorphism of this vector bundle plus the connection with its Frobenius pullback. Where by Frobenius, I mean you pick some lift of absolute Frobenius. So there's a result of Elkique that implies that some lift actually exists, but it's also okay if you just make X small enough for there to be a lift. Say by making X small enough that it has an etale map to a projective space, and then kind of taking the obvious Frobenius lift on projective space and then pulling it along the etale map. It will turn out that what I'm defining here is a category that doesn't actually depend on choices. So it doesn't matter what P you take, it doesn't matter what sigma you take, there will be natural isomorphisms of these categories or equivalences between these categories as you vary these choices. Or a better way to say it is if you make a site that sort of captures all of these choices and define a crystal on that site, then this category is the same as the category you make on the site. So that's a sort of more robust way to say that this category doesn't depend on any choices. And in particular, you can kind of sheafify and make a definition for non-affine X, but you're free to think about affine X for the purposes of this talk. That won't cause any problems. And a similar definition applies if instead of FP, you work over some other base field. So in particular, if you work with a base field little k, my algebraically closed field of characteristic P, you can do the same thing. Instead of ZP, you take the Witt vectors over little k and you do something similar. So that means I can talk about isocrystals both on X and on XK. And so I'm going to want to talk about isocrystals on XK modulo phi k, which will mean taking an isomorphism with the phi k pullback, but we'll come to that in a moment. Let me recall that if you take convergent F-isocrystals over a geometric point, then the Diodenay-Manin theorem gives you a classification of these things. The Newton polygon turns out to be a complete invariant. So there's a kind of discrete invariant for these things. There's not even any problem with extensions. The category is semi-simple. That's only true over a geometric point, though. It's not true over more general bases. But what is true over, say, X is that the Newton polygon defined by, for every point, you base change to a geometric point and use Diodenay-Manin to read off what the Newton polygon is. That turns out to define an upper semi-continuous function on X. So you get a stratification by these things. And if the Newton polygon is constant, then you get a filtration which kind of separates the slopes of the Newton polygon. So you get a filtration where the successive quotients each have a constant Newton polygon consisting of one flat segment, and the slopes of those segments go in order. Usual convention is that they go in ascending order, which is, I guess, kind of backwards to the convention from slope theory vector bundles, but it's pretty well entrenched. So yeah, so this is saying that okay, it's somehow close. So this upper semi-continuity means that there's a generic value for the Newton polygon. So there's an open dense subset where the Newton polygon takes a single value, and then there are some exceptional sets where it jumps. So and on this open subset where you have a constant Newton polygon, you can write the thing as an extension of things of a single slope. And these things of a single slope you can kind of describe in terms of Galois representations. So let me in particular state the form where the slope is 0. So an object is said to be unit root, or sometimes etale, if the Newton polygon is constant with all slopes 0. Okay, and in that case, there's equivalence of categories, tensor categories actually, between these unit root convergent F-isocrystals and something hopefully more familiar, continuous representations of the etale fundamental group on finite dimensional QP vector spaces. So this looks much more like lisse L-adic sheaves. This is basically, if I replace P with L, this is essentially a lisse L-adic sheaf. But what happens in this picture is that this gives you a sort of piece of the category that you want. But there's more in this category than just these things. And for example, there are extensions between guys of different slopes. Now the other slopes you can deal with similarly. There's a kind of twisted version of this statement for objects where the Newton polygon is constant and the constant value is a flat polygon with a single slope that's not 0. It's equal to some other value. There's a kind of twisted version of this that applies. It actually reduces to this statement. So roughly speaking, if you have a constant Newton polygon and it's isoclinic, it consists of a single line segment, then this object is related to some Galois representation. The problem is on my previous slide, the kind of extension class between these things is not itself described by anything involving Galois representations, because somehow you're comparing these pieces of different slopes. The description in terms of Galois theory is incompatible with the discrepancy between the different slopes. So you really have to do something to understand the extensions in this filtration, but at least the individual pieces are things to which Galois theory applies. Okay. So some more. I need some more background before I get to Drinfelds lemma. So this is a statement that it is supposed to be analogous to something about lisse sheaves. If I take an open dense subset of X, then restriction of convergent F-isocrystals from X to U is a fully faithful functor. So if you have two F-isocrystals on X, any morphism defined in an open subset actually prolongs. So this is sort of corresponding to the fact that in lisse sheaves, something like this is true because if you take pi1u, this has pi1x as a quotient. Right, the pi1u is you're imposing some unramifiedness condition at the points of view, and then if you add more unramifiedness conditions, you're passing to a further quotient. However, the p-adic statement is not a direct consequence of this, essentially because of what I said earlier. It's not the case that objects of this p-adic category are completely described by Galois theory. So there's some kind of delicate p-adic analytic arguments that were inspired by de Jong's work on crystalline Dieudonné theory. This was stuff I was working on back around the time of my PhD thesis. But anyway, this is an important thing that we're going to be using quite a bit as we go along. So I want to put this on the table, as this is not easy to prove, but it is true, and it will be a key tool. Okay. Oops. Okay, so now we're ready to talk about Drinfelds lemma. So something funny is happening with my slides. So now I'm ready to talk about convergent F-isocrystals on xk modulo phi k. And as promised, this is some kind of equivariant category. So I take an object in this category will be a convergent F-isocrystal on xk plus an isomorphism with its phi k pullback. Now remember, by definition, these objects already come with an isomorphism with their total Frobenius pullback. So right, xk has kind of a partial Frobenius on x and a partial Frobenius on k, which when you compose them in either order gives you the total Frobenius on x, the absolute Frobenius. And so I started with an object that has an action of the absolute Frobenius, and I'm adding an action of one partial Frobenius, so it actually has an action of the other partial Frobenius on as well, the one on x. However, I want you to focus on the phi k one. So yeah, and so an object in this category is one of these convergent F-isocrystals plus an isomorphism with its phi k pullback. A morphism is, of course, a morphism of the convergent F-isocrystals, which is phi k equivariant, as well as of course, being regular Frobenius equivariant. And so there's a pullback functor, but here's the thing, that this is not an equivalence of categories. And the reason is because you can do things like, you can take an F-isocrystal on X, an F-isocrystal on spec K. You take the F, right, this thing is characterized, this F is characterized by its Newton polygon. You take it not to be unit root, and then you take this external product. And that's not going to appear in this essential image of pullback. The pullback is essentially doing things like E goes to E box product with the trivial F-isocrystal on X, on spec K. So so there's a whole slope theory on the spec K side that you're missing if you take pullback. When you pull back, you're essentially getting objects that are unit root with respect to spec K. And this category imposes no such restriction. So what you essentially want to show is that this is the worst that can happen. That somehow all of the objects are accounted for, more or less, by taking these kind of external products. So that's, I'm going to give you a more precise statement that actually says this, but this is what I want you to have in mind, is that I want to know that all of the objects in here come from things like this, E box times F. Maybe you have to take some subquotient of one of these. But kind of you find all the objects all the objects are generated by things like this. Okay?
Kiran,
Yes, go ahead. Yeah.
The pullback functor is fully faithful by what you mentioned earlier.
It is fully faithful. Yes.
Oh.
That will essentially follow from a kind of judicious application of this theorem.
Okay.
No, actually it's easier. I guess it's a sort of Galois descent in this setting. But yeah, so the pullback functor is fully faithful, and we'll see later. We've already seen why it can't be essentially surjective, but we'll give a description of this category that sort of shows you what the kind of the corrected version of this statement is. Okay, so yeah, so if I take an object in this category, I mean, I can forget the partial Frobenius action, and then I get a stratification by Newton polygons. However, if I then remember that there's a partial Frobenius action, that tells you that the stratification of xk given by the Newton polygon of this object is invariant for the action of phi k, right? Because the stratification is uniquely determined by this object, and this object is unique, it's isomorphic to its Frobenius, its phi k pullback. So the stratification has to be phi k invariant. And that's a pretty strong restriction. Using one of the earlier version of Drinfelds lemma, that tells me that the stratification is actually pulled back from X.
Okay, Ron.
Was there, okay, I thought I heard a question. Yeah, so that's a pretty strong statement. That's saying that if I take a general object of this category, the stratification will be by just random closed, locally closed subschemes of xk. Here I'm saying when I take one of these objects, those closed open subschemes are actually defined over fp. Okay, now suppose this means that, for example, I can find an open dense subset of X where I get a constant Newton polygon, which would not have been true had I not done this step, right? I would have taken an open subset of xk, which doesn't necessarily come from X. So now I can kind of go to an open subset of X where I have a constant Newton polygon, and then the slope filtration of E will itself be stable under the action of phi k, again because it's unique. It's uniquely determined by the underlying object without the phi k action. And if I take one of the pieces, say for example this thing has a unit root subquotient, then that will correspond to a p-adic representation of the fundamental group of X with an additional action of phi k. Sorry, this, no, I think that's right. It is actually X. That's, I mean, yeah. So it actually, you sort of a priori you get an action, you get something of pi1 of xk, but you have some invariance property. It's isomorphic to its pullback by Frobenius, but some sort of action of phi k on the underlying representation space does sort of persist. Okay. So this is very helpful. This allows me to prove some theorem like this. And so this is in some sense the main theorem, except it's stated for the wrong category. So this is the corrected version of the statement I had 2 slides ago. It says that if you take an object in this category, it has a sort of relative Jun-Neymannian decomposition. So I have a decomposition indexed by rational numbers, and each summand, it comes from an object of the isocrystal category over X, which itself carries an extra structure. It carries an endomorphism such that F to the S is P to the R, and then you kind of define, you sort of take this object on X, and you define an object on XK by pulling back, and then you kind of give it a twisted action of phi k using this F. And so the point is that you should have sort of taken all those additional pullback functors as well as the standard one, which corresponds to d equals 0, and that accounts for everything. Every object actually splits into pieces that come from these different twisted pullback functors. So this is the modified version of Drinfelds lemma that applies in this case. Is that okay? You're allowed to twist the pullback by by having a non-trivial Newton polygon for the phi k action, but that's the worst you can do. Okay. Okay. So this is in fact most of what I need to know, but I do have to modify the statement because I somehow used the wrong category. Convergent F-isocrystals turn out not to be well behaved from the point of view of trying to construct a V cohomology theory. For example, if you take the underlying isocrystal without Frobenius and you take cohomology of it, this is what you normally would want to use to do V cohomology. These are not finite dimensional QP vector spaces. So this is kind of a problem. And this ultimately comes from the fact that the Poincare lemma fails for rings like the ring of strictly convergent power series over QP. Differentiation is not surjective because you can have things that you can take power series where the powers of P grow kind of slowly, and you do introduce some denominators when you anti-differentiate, so you might mess things up. Now, there's a standard way to fix this, which instead of working with a closed disk, you work with some kind of overconvergent thing. Basically what you do is you replace the formal lift with what's called a weak formal lift. And then kind of mutatis mutandis. For example, if X is affine space of some dimension, and you lift it to the formal affine space, so then the global sections of the structure sheaf on the formal lift will be strictly convergent power series over ZP. This weak formal lift is an object in some category of weak formal schemes, and the global sections of the structure sheaf are power series that converge on some polydisk of radius strictly greater than 1, but you're allowed to vary the radius depending on the series. And the point is that when you take, say, partial differentiation with respect to a variable on a ring like this, it is a surjective morphism because you're only doing when you anti-differentiate, you're only introducing some logarithmic denominators that maybe affect convergence at the boundary of the disk, but if you're allowed to move the boundary a little bit, that takes care of matters. So that's sort of how you fix the definition for affine space, and in general, weak formal schemes are going to be things that come from quotients of rings like this. And then their p-adic completions will give you traditional formal schemes. So this is a sort of a standard operation that's people have been using for some time. It's important to point out that there is again a statement, this is backward, the restriction functor from overconvergent F-isocrystals to convergent F-isocrystals, so the dagger's in the wrong place. That restriction functor is fully faithful. but I should point out that it does not necessarily preserve irreducibility. That was actually true in the convergent case for restricted to an open subset. But the point I wanted to make here is that slope filtrations don't generally exist in this overconvergent category. So if you have something with a constant Newton polygon, you can't separate it into pieces of a single slope. You have to go to the convergent category, do it there, and hope that you're in some situation where a statement like this allows you to transport the information you want back. There is a way to describe exactly what's going on here, but the sort of the conjunction of these two statements can actually be made in a more affirmative way. It has something to do with what's called Kruse parabolicity conjecture for Tanaka and monodromy group, which is the theorem of Morpho-D'Adezio. But I won't need it here. I just want to state this theorem and then can give you one sentence about it, because time is a bit short. Yeah, so basically, if you just replace convergent F-isocrystals with overconvergent F-isocrystals in my previous theorem, it works, and basically it reduces to the convergent case. So you can decompose E as a convergent object. The projectors in this direct some decomposition will automatically propagate back to the overconvergent category. You have to check that the objects that you're making, well, that you know that their underlying convergent F-isocrystals are pullbacks from X, but you can again use this kind of full faithfulness construction to show that the objects that you got on X actually are also overconvergent. Basically, because when you base change them back to K, you have an isomorphism with an overconvergent, and you can descend that. Okay, so yeah, so this is most of what I need. Well, let me just finish by making some comments, kind of tying what I said earlier. So yeah, if you want to talk about constructible things, you have to view objects here, right? These are supposed to be like vector bundles with a connection. Well, vector bundles with a connection you can think of as left modules for some ring of differential operators. And so Abe describes some category of D modules which give you sort of a p-adic analog of the constructible derived category and admits a good 6 operators formalism. And okay, there's a Holland, yeah, you need some holonomicity condition in order to get this 6 operators formalism to work well. And yeah, the statement of Drinfelds lemma kind of formally transports to that setting. I say formally, I'm sort of counting on Daxin to write this part down, because it's not formal for me, but it's formal for people who know what they're doing. And the key point is kind of similar to something I said earlier. If you have one of these objects, some object in the constructible derived category over xk modulo phi k, well, you get a canonical stratification where you have lisse objects. That's of course not complete information to reconstruct the constructible object, but it's sort of an important component. And that stratification again descends to X because it's somehow canonical, so it's stable under the action of partial Frobenius. That's sort of the moral of the story is structures that are stable under partial Frobenius descend from K to FP. And so in this case, the kind of the stratification by lisse objects of a constructible object has such a stratification. I mean, that stratification is canonical. So when you have an object that's defined over xk modulo phi k, the stratification descends to X, and then you can use that ultimately combined with what I said earlier to show that the whole thing actually is an object that comes from X, well, up to this appropriate modulo this twist about involving the Newton polygon with respect to phi k. Yeah, I mentioned, I put a footnote here. The objects here, these are really, this is a QP linear category. If you want a QP bar linear category, which is what you're supposed to have in the end, the way you do it is you do the following. For every finite extension of QP, you just consider objects of this category, together with a formal action of multiplication by this larger field. So you kind of tensor up from QP to this larger category, to this larger finite extension of QP, and then the QP bar objects are just the 2 colimit over all possible finite extensions inside here. Right, and that's sort of agreed that's not the way you would normally describe least QL bar sheaves, but it is a way you could have described least QL bar sheaves. They always come from some finite extensions QL. Yeah, and I'll just mention to conclude that there is a version of Drinfelds Dilemma, both classically and also in this context, where instead of taking a product with K, you take a product of a bunch of different schemes over FP. It could be 2, it could be more than 2. If you deal with the case for n equals 2, then you can kind of inductively retrieve the general case. Yeah, so these are going to be objects that carry actions of all but one of the partial Frobenius maps. In this picture, this X has n partial Frobenius maps. So specifying an F-isocrystal gives you an action of the total Frobenius, which is the composition of all of the n partial Frobenius maps in any order. So you have to give actions of the individual Frobenius maps to get kind of an object in this defined over this quotient object, but you really need all but one, because then you infer the last one by kind of the condition that you want the total action to be the one that you specified on the underlying category. And roughly speaking, this is giving you a statement along the lines of the pi1 of x divided by n minus 1 of the partial Frobenius maps is the product of the fundamental groups over here. But you have to make this statement in a more Tanakian way to make it correct. In particular, I didn't say this earlier. Maybe I should have said this earlier. You would have, had I been talking instead of least sheaves earlier, had I been talking about they sheaves, then there would have been something more like this phenomenon with the Newton polygon showing up. So you really want to talk not about pi1s, but more about they groups. And so you have to kind of tweak things on the p-adic side so that you have something that looks more like a they group. And then you can make an assertion like this. All right, I think that's all I've got, so thank you.
Thanks for the talk. Do you have any comment, any question? Or?
I'm intrigued by what you said at the beginning about Vincent Lafforgue's construction. I'm wondering whether there is an analog in this p-adic setting of the pseudo characters.
So I have to say I haven't really thought much about Vincent Lafforgue's construction other than sort of what I needed to know in order to be able to state this. I mean, I think the expectation is that you should have kind of a whole parallel story in the p-adic world. But I have not thought about that. I don't know if Daxin has gotten as far as thinking about that either. But that's something, the hope is that we could kind of imitate imitate everything that happens with L-adic coefficients. Yeah, so I don't know what so I guess really the question is, what is the analog of a pseudo character in the world of isocrystals? And I actually don't know. What is a sort of analog of just thinking about traces for an isocrystal? Yeah, I have no idea, to be completely honest. I feel like there should be something, but I mean, for unit root things, presumably you can use an actual pseudo character, but in general, I really have no idea whether there should be a good analog or what there should be. I mean, I hope there's a good analog, but that's a great question. Sometimes the best questions are the ones that completely stump the speaker. So thank you.
Someone have another question or comments?
I was just curious about the terminology. You start with convergent F-isocrystals. What does the convergence refer to?
So, well, I guess the way I would say it is that if I go back to this slide, right, convergent isocrystals are made out of power series that are convergent on a closed polydisk, and overconvergent isocrystals are made out of this ring, which consists of power series that overconverge. They converge in with a larger radius.
Hmm.
So that's generally where that terminology comes from. It's referring to convergence on a closed disk versus convergence on an unspecified larger disk.
So you wouldn't just say F-isocrystal. You would start with convergent F-isocrystal.
Well, I mean, I guess originally there was a distinction between F-isocrystals that were defined in terms of the crystalline site versus convergent F-isocrystals that were defined in terms of the convergent site. Right, so F-isocrystals on the crystalline site, well, you take F crystals on the crystalline site and then you just invert P in the morphism categories. And right, there's a comparison theorem by, I guess, Ogus, or Berthelot and Ogus, that says that those two notions of F-isocrystals agree. So yeah, so if you were not say convergent or overconvergent, it would imply that you're working directly with the crystalline site. But there's no analog, there's no version of overconvergence that makes sense with the crystalline site. I mean, you can make an analog of the convergent site that handles overconvergence, but there's no good analog of the crystalline site because the crystalline site really only sees things sort of modulo 1 power of p at a time. And sort of the difference between overconvergence and convergence is washed out when you look modulo 1 power of p at a time, because that effectively means you're taking p-adic completions.
Okay, so please, thanks again the speaker.